Hello everyone. Uh, it's my great pleasure to give a talk on this seminar about classical notes and virtual notes, and also I would like to thank Micah, Sujoy, and Robert for inviting me to give a talk here. So today I will talk about chord index type invariance of virtual notes. Roughly speaking, this is a survey talk about the index type invariance of virtual nodes, and first I will give a quick introduction to virtual nodes theory. Okay, let me begin with how to count the crossing points. If we are given a node diagram, I think it's very natural to consider to define a node invariant by counting the crossing points. But obviously, we can find that this integer is not an invariant because the first and the second randomness move will change this integer. So to overcome this difficulty, one can define the crossing number of a node to be the minimal crossing number of all among all the node diagrams that can be used to represent this node. However, in general, it's quite difficult to find the crossing number because for any node you can find infinitely many different node diagrams. So we can use the sign of each crossing to enhance the counting. For example, we can consider the signed sum, and we can use these two pictures to associate a positive sign or a negative sign to each crossing point, and then we can get another integer. We usually say the rise of the node diagram, and it's easy to find that this is invariant under the second and the third randomness move, but not the first one. So our main goal is to define a weighted signed sum by assigning an index to each crossing point, such that it is also preserved under the first randomness move. Here is an example. For example, the famous Kondo cocycle invariance can be defined in this way. If we are given a finite Kondo and A is an abelian group and K is a node diagram, for any fixed Kondo coloring, we can choose a Kondo 2 cocycle. And then we can use this Kondo 2 cocycle to assign an index, which is an element of the abelian group, to each crossing point. Here, the two chords, two arcs, XC and YC, can be defined in this way. Maybe I need to draw it here. So, if this is the crossing point C, and we call this arc XC and this one YC. So for this choice, we can assign an index phi fxc and fyc to this crossing point C. And then the Kondo cocycle invariant can be defined in this way, which is an element of the group ring ZA. And here the W denotes the sign of C. Actually, in order to recover the classical fact that reduced alternating node diagram has minimal crossing point, in joint work with Hongzhu Gao, we introduced another version of Kondo cocycle invariance, which we call it a positive Kondo cocycle invariant. We want to use this kind of Kondo cocycle invariant to recover this result, but however, we found that both the positive version and the original version of Kondo cocycle invariance, they just reduce to the coloring number if the abelian group A has no torsion. But it is still hopefully to use this kind of technology to reprove this result, which was originally proved by using the Jones polynomial, because for alternating knot, the closing number is always actually the determinant of the knot is always greater than the closing number. So it is possible to consider the dihedral condo, and maybe you need to make some modification, and then you also can. It is possible to reprove this result, but at present I don't know how to deal with it. Okay. Now let us turn to the theory of virtual knots. When we say a virtual knot, actually we mean an embedding of one sphere into the sected, closed, and oriented surface. And we say two virtual knots are equivalent if and only if their surface embedding are equivalent up to isotropy, diffeomorphisms of the surface, and also you can add or remove some empty handles. And usually we can just use a regular projection of the knot and the plane to represent this virtual knot. The only difference is besides of the real crossing points, now you can have some virtual crossing points. And from the viewpoint of the nodal diagram, it was proved by Luce-Kaufmann in the first paper of virtual knots that two virtual knots diagram represents the same virtual knot if and only if they can be connected by finitely many generalized random master moves. So totally we will have 7 kinds of generalized random master moves. And you can see that the first 3 are just those the classical random master moves, and then the rest generalized random master moves involve some virtual crossing point. Also, we notice that we have 2 kinds of forbidden moves. We call it omega 3O and omega 3U, and it was independently proved by Kajinobu and Sam Nielsen. If you are if we are allowed to use both of these 2 kinds of forbidden moves, then any virtual knot can be transformed to the unknot via some forbidden moves. However, if we are just allowed to use only one of them, then we cannot achieve this, because if we are only allowed to use just one of them, then we get the so-called invariant knot theory, and this was first introduced by Fenn and some his co-authors in the study of the automorphism of free condo. Here is another motivation to introduce the virtual knots. We know that every classical knot diagram corresponds to a unique Gauss diagram. However, not every Gauss diagram can be realized as a classical knot diagram. But you can always realize each Gauss diagram by actually infinitely many virtual knot diagrams. Sometimes you have to add some virtual crossing points, and it was proved that there is a one-to-one correspondence between the virtual knots and the Gauss diagrams modular the classical random master move. I think the benefit is from the viewpoint of Gauss diagram, you cannot see the information of virtual knots, but actually you can also read some information about the you can read some information about the virtual crossing points from a Gauss diagram, even you can see it from it, because we only draw the real crossing points on a Gauss diagram. Here are some remarks. I think the reason why we care about Gauss diagram is we can use the Gauss diagram to calculate the phenotype invariance. Actually, it was proved by Gauss law of Polyak and Viro that or finite type invariants can be formulated in the form of Gauss diagrams. And actually, they also proved that the set of classical nodes is embedded in the set of virtual nodes. They proved that virtually equivalent classical nodes are classically equivalent. And recently, Bowden and Nagel, they proved that virtually concordant classical nodes are classically concordant. Okay, so next I will introduce how to define virtual node invariance from a Chord index. First, we need to define integer valued Chord index derived from Gauss diagram. Assume we are given a Gauss diagram and we choose a chord of it. We say chord C, and then we can consider all the positive chords crossing C from the left side to the right side, and we will use R plus to denote the number of all these positive chords crossing C from left to right. And in a similar way, we can define R minus, L plus, and L minus. And then by using these four integers, we can define the index of C to be R plus minus R minus minus L plus plus L minus. So you can associate an integer to each chord in a Gauss diagram. Or equivalently speaking, we can always associate an integer to each real crossing point in a virtual node diagram. And I would like to remark that if this is a classical node diagram, then the index of each crossing point is 0. Yeah. So the index is trivial for each crossing points in a classical node diagram. However, for virtual node diagram, it is sometimes it is non-zero, and this kind of index behaves quite well under the random master moves. More precisely, the crossing point in the first random master move has index 0, and the two crossing points in the second random move have the same index, and the indexes of the three crossing points in the third random master move are preserved under the random master move. So, and actually this index can be considered as a generalization of the Kaufman's otherwise. I'm sorry, here I have a typo here. Otherwise, okay. And the Kaufman's otherwise actually he associated a parity to each chord in a Gauss diagram, and also this index is a generalization of Heinrich's non-negative index. So I will show you some application of this chord index. The first one is you can use this to define a polynomial invariance of virtual nodes. We call it the Rice polynomial. The Rice polynomial is defined in this way. Roughly speaking, we are just counting the sum of the signs of all the crossing points with the same index, and we just write it in the form of a polynomial, and we call it the Rice polynomial. It is worth to point out that actually this kind of polynomial was independently introduced by several other people, and it is not difficult to find that all these polynomials are essentially equivalent. Yeah. So in my talk, I would like to use the name Rice polynomial, and by using this definition. Okay. Here are some remarks. The first thing is this kind of polynomial is very easy to calculate, and it is also very sensitive to the symmetry of virtual nodes. You can use this to distinguish some virtual nodes from the mirror image, and also you can use this to distinguish some virtual nodes from the inverse. Yeah, I mean you just reverse the orientation. And the second one is just we mentioned before, even you cannot see the virtual crossing points on a Gauss diagram, but the Rice polynomial, which was derived from the Gauss diagram, can be used to provide some lower bounds for the real crossing points and the virtual crossing points. And also, we can extend the notion of phenotype invariant from classical nodes to virtual nodes, and it was proved by Dai that the Rice polynomial is a phenotype invariant of degree 1. Also, this kind of polynomial invariant can be recovered from the generalized Alexander polynomial. It was proved by Merrill in 2016. Recently, it was proved by Bolden, Chrisman, and Gauss that the Rice polynomial is a concordance invariant. And last year, Nakamura, Nakanishi, and Sato, they gave a local move description of this kind of polynomial invariant. Actually, they proved that two virtual nodes have the same Rice polynomial if and only if these two virtual nodes can be related by some shear moves. Here I give two pictures here, and for more detail, the reader refer to the paper of Nakamura, Nakanishi, and Sato. Okay. The second application is about the chord index hierarchy. I think this was first noticed by Turiev. And we just use the name by him, so we call it the covering of virtual nodes. So if we use the G to denote the set of all Gauss diagrams, and we use K to denote the set of all virtual nodes, then we define a map Pn from G to the surf. And the definition is we just remove all the chords of a node diagram whose indexes are not divisible by n. So from the viewpoint of the virtual node diagram, we just replace each real crossing point. If the index is not divisible by n, then we just replace the real crossing point with a virtual crossing point. And it was first proved by Turiev and later rediscovered by Im and King that the map Pn induces a well-defined map from virtual nodes to virtual nodes. So it immediately follows that for each virtual node K, we can have a sequence, say P0, P1, P2, P3, and this set is an invariant of K. And I would like to remark that here the P1 is nothing but the K itself, and for each given virtual node K, for sufficiently large M, this sequence will stable. I mean, all the rest virtual nodes are all P0 because the crossing number, the real crossing number is finite. Yeah. So if we have any given virtual node invariant A, then we can use this to get a sequence of node invariants. For example, you can use the Alexander polynomial or Jones polynomial or the Miyazawa polynomial. So you can get a sequence of node invariants by using the chord index. And very recently, it was also proved by Nakamura, Nakanishi, and Sato that this map is the map from K to P0, P2, and Pm for some integer m. This map is surjective. So it means that for any given node, P0, P2, Pm, you should notice that here there is no P1 here because P1 is nothing but the node K itself. You can always find the node K such that this map you can find virtual node K which is the pre-image of this map. Yeah. Yeah. Okay. So this is a result, a recent result of the computer and Hennessy and Seto. The third application is we can use the Chord index to define a so-called indexed condo. Okay, I will tell you what is an indexed condo. An indexed condo is a set index Q, and we have a sequence of binary operations. Recall that in a condo you have just only one binary operation, and for these binary operations we need them to satisfy the following conditions. And the first one is the star 0 for each element A star 0 A is equal to A, and for each I star I is invertible. So it means that you can always find the unique element A such that A star I B is equal to C. And the third one is a modification of the right distributivity. And you find that the index, if the index is I and the second is J, and on the right side you have index J, I, and J minus I. Actually, all these conditions can be derived from the random moves. Yeah, just like the condo. Yeah. Here are some examples. If we have a condo, then we can sort this condo as an indexed condo if we define all the operation star I is equal to star. And another way to regard the condo as an indexed condo, we can introduce the star 0 is equal to star, and for any other star I, we just use the trivial operation to define this. And also we can define, we can call it indexed identity condo, and we define A star I B is equal to TA plus 1 minus TB plus I for some integer I. And in general, if we are given a group and we have a phi, which is the automorphism of this group, and we can choose an element from the center of this group, then this group can be regarded as an indexed condo by using the operation A star I B is equal to phi AB inverse and B J to the power of I. Okay, so here are some examples of indexed condo. The reason why we introduce the notion of indexed condo is we can use this to define a coloring invariance of virtual nodes. The rule is if we have a closing x, and if the index of x is I, then we require that the color on the right arc C, the C is equal to A star I B. So you can see why here we have the index I, and why the index is important here. And also you can extend the condo coloring invariance, and also you can define the so-called indexed condo cocycle invariance, and but I will omit all the details here. So you can also define some similar indexed condo cocycle invariant, just like the condo cocycle invariant. Yeah. So this is the third application. So in the second half of my talk, I would like to discuss what is a Chord index. Here I would like to introduce definition of a chord index. When we say a chord index, we mean it can be an integer or a polynomial or a group or an algebra or something else, such that we can associate such integer or polynomial or a group to each real closing point, such that all the closing points in the first random move have the same index, and the two closing points in the second random move have the same index. Because in the second random move we have two closing points there, so we are required these two closing points have the same index, and the index of each closing point in the third random move is preserved under the third random move. So if we can find a chord index satisfy all these three conditions, then we can define a signed formal sum, and which is a virtual not invariant. So that's the reason why we require a chord index to satisfy these three conditions. Of course, the chord index mentioned before, in the definition of the rest polynomial, is a typical example of a chord index. But actually, we can find some more general examples. I will show you later. A remark is actually this chord index is motivated by the chord parity axioms introduced by Mantelov in about 2009, and he defined he just associate a parity, just 1 or 0 to each real closing point. So the next question is how to construct a chord index. I will give you 3 examples. The first one is an index function, and this index function can be regarded as a generalization of the chord index defined, used in the rest polynomial. So, if we have a chord in a Gauss diagram, and we will use R1 to Rn to denote the chords crossing C from the left side to the right side, and we will use L1 to Lm to denote the chords crossing C from the right side to the left side. And here we also need a map. We will use phi to denote the canonic quotient map from Z to Z modulo the absolute value of index of C. And now we can define the index function of C in this form. Strictly speaking, this is not a polynomial, because the exponent is a little weird thing, because it lives in Z modulo the index, the absolute value of the index of C, but it is well defined. Yeah, you can check that it is well defined, and in particular, if we set S to be 1, then we can re-obtain the chord index that's used in the rest polynomial. So we can regard this index function is a generalization of the chord index. So the main result is this index function. This index function is a chord index. I'm sorry, I think I made some mistake on the time here. I guess the time should be 2017. Yeah, sorry. Okay. The first thing is this index function is a chord index, so we can use it to define a virtual knot invariant, and we call it the transcendental function. The definition is quite similar to the definition of the Rice polynomial, but it is much more powerful. First, I would like to remark that this transcendental function is motivated by the zero polynomial, which was defined by Zhiyun in 2015. And although we use two variables here, s and t, actually, if you just replace s with t, this invariant will not be weakened. And the last one is just we mentioned before. If we set s to be 1, we just obtain the chord index. So if we set s to be 1, then we can get a polynomial which is essentially equivalent to the Rice polynomial. Okay. Here is an example. This is a Gauss diagram of a virtual knot, and by direct calculation, we can find that the transcendental function has the form of this. But for this example, the Rice polynomial is trivial, so it means that we can use this to. So it means that this transcendental function is real, has much more powerful than the Rice polynomial. Okay, for the second example, I will give a non-intrinsic construction of the chord index. For this construction, we need to use a given finite biquandle. Yeah, we will use a finite biquandle to construct a chord index. So here's the plan. First, I would like to recall the definition of a biquandle. A biquandle, BQ, is a set with two binary operations, and we use a star and a circle to denote these two binary operations. Also, from the Reidemeister move, we require that these two binary operations they satisfy these three very complicated conditions. But you can just write them down from the Reidemeister moves. So here's the rule of the coloring. So if we have a virtual knot diagram, and now we can associate an element to each semi-arc. Yes, to each semi-arc. So this is the different from the coloring of quandle, because for a quandle we just assign an element to each arc, but for a biquandle we associate each semi-arc with an element of the biquandle. And this picture tells you how to define the coloring. And the definition guarantees that the coloring number, the number of all different colorings, is a virtual knot invariant. I mean, it does not depend on the choice of the virtual knot diagram. For a given finite biquandle, we can consider the group GBQ. The meaning is we require that the contribution from the crossing point in the first Reidemeister move is 1, and we also require that the contribution from the before the third Reidemeister move, I mean the product of the contribution from the three crossing points before the third Reidemeister move is equivalent to the product of the contribution from the three crossing points after the third Reidemeister move. Actually, if we have any homomorphism from this group GBQ to an abelian group A, then you get a biquandle two-cycle. But here, we need to consider a subgroup of this GBQ, and we use the red GBQ to denote the subgroup. The main idea is we are not just satisfied by the product of them are equivalent. We also require that the contribution of each crossing point is preserved under the third random master move. So that's the reason any element in this red GBQ is also an element. Actually, it defines equivalence class from the original GBQ. So by using this new GBQ, we can define a chord index. If first we need to fix a coloring, we need to fix a bicontour coloring, and now we can assign a weight. We just use WF, which is nothing but the XY, but the position of X and Y depends on the sign of the crossing. So if the sign is positive, and so if the sign is positive, we require that this is X and this is Y. On the other hand, if the sign of this crossing is negative, we require that this is X and this is Y. Okay. Now we can define the chord index of crossing points to be the sum of all these Boltzmann weight, and also this is an element in the group ring ZGBQ. So now we define a chord index which is an element of this group ring. So just like the definition of the Rice polynomial, we just count the sciented sum of all the crossing points with the same chord index, and so we can for each element in the group ring we can define an integer. We call it AG. So the result is for any finite bicontour, AGK is a virtual not invariant. And also we can use by choosing some bicontour, we can use this to recover the chord index used in the definition of Rice polynomial. Let me show you one example. Because in the original definition of the Rice polynomial, you can only define a polynomial invariant for virtual knots, but for virtual links, you have to make many modification, and sometimes you will face some problems. But now, this kind of definition is valid for all virtual links. So let us consider the following two-component virtual link L. So you can see that we have two components here, and we just use a very simple bicontour X, which consists of just two elements, 1 and 2, and here we define the binary operations. It is not difficult to find that for this bicontour X, the group Gx is nothing but a cyclic group, and we will use the T to denote the generator of this cyclic group, and T is just the element 1, 2, or just 2, 1. And you can find that we have totally 4 different colorings here, and the index of, because now we have 3 crossing points here, A, B, and C, the index of A and C are both equal to 1 plus 1 plus T plus T, and the index of B is equal to T plus T plus T plus T. So we can get two non-trivial not invariants, and A 1 plus 1 plus T plus T is equal to 2, and A T plus T plus T plus T is equal to 1. And for all other elements in the group ring, the associated invariant A is 0. So also you can get the a lower bound for the real crossing points for this virtual link, because now you have 3 crossing points here, so you can conclude that the real crossing points of this virtual link is exactly 3. Okay. So this is the second example, and because now we are using a biquandle, a natural question is if we replace the biquandle with a quandle, of course we can also get an invariant. But however, we can prove that if we are using a quandle instead of a biquandle, then all the crossing points will receive the same index. So it means that you cannot get any new information. You can just get the current number. So here's a question. At the present, we don't know whether we can define a non-trivial chord index for each crossing points in a classical node diagram by using some suitable biquandle. Yeah, I think for quandle we can't find a non-trivial chord index, but at present I don't know whether this works for biquandle. Maybe we can prove that for each finite biquandle, we can get a non-trivial chord index for crossing points in a classical node diagram, but at present I don't know how to prove it. Yeah. Okay. Here's the last example. Because in the second example, we can use a biquandle to define a chord index. It means that you have to use another structure, a biquandle, a finite biquandle. But here, I would like to introduce an intrinsic construction. So without using a biquandle, we just consider the virtual node itself. Okay. Recall that there are some variation of virtual nodes. For example, we can consider the flat virtual nodes. Roughly speaking, it can be defined as the all the equivalence classes of virtual nodes up to crossing changes. Yeah. So if we are allowed to switch each real crossing points, then we get the set of flat virtual nodes. Yeah. This is also a non-trivial node theory. Let us use M1U to denote the free J module generated by unoriented flat virtual nodes, and we use M2 to denote the free J module generated by oriented two-component flat virtual links. And also, there is a canonic map from the set of virtual nodes to the set of flat virtual nodes. We just replace all the crossing points in a virtual node diagram by flat crossing points. So you can now you can define a map from the set of virtual nodes to the set of flat virtual nodes, and it is possible that two different virtual nodes may be mapped to the same flat virtual nodes. Yeah, and also we use the virtual node diagram here, but this map is a well-defined map. Okay. Now, so if we have a virtual node and C is a virtual crossing point of K, here the crossing point C it could be a positive one or a negative one. So we just draw it in the flat form. And now we can choose two kinds of smoothings, one smoothing and zero smoothing. And if you apply the zero smoothing, you can get another virtual node. We call it KC. And if you apply the one smoothing, you can get a two-component virtual link. We call it LC. So it depends on the choice of the crossing point C. In a joint work with Hongzhu Gao and Meng Jianxu, we found that both the image of key C under the map F and the image of LC under the map F, and the first one is element in M1U and the second one is element in M2. Both of these flat virtual nodes or flat virtual link, they are all chord indexes. Yeah. So now we find a chord index which is a flat virtual node or a flat virtual link, not just a number or a group or a polynomial. Yeah. We find we can define a chord index which is a flat virtual node or flat virtual link. And by using this, we can define two invariant of virtual nodes K. The first one we call it Fk, and the second one we'll call it Lk. And the first one is an element in the set of M, in the module of M1U, and the second one is an element in the module M2. And because these two are chord indexes, so it follows that F and L are both virtual node invariants. So it means that if you have a flat virtual node invariant, you can composite with this map F and L, so you can get many useful virtual node invariants by using some flat virtual invariants. Yeah. Also, the first remark is our first example, the Rice polynomial, also can be recovered from definition of L. Yeah, you can read the Rice polynomial from the invariant Lk. Actually, the motivation for introduce this kind of chord index is in 2018, Carroll, Prohaka and Verselin, they introduced a sequence of two variable polynomials, L and K, and all the sequence of these two variable polynomial invariants can be obtained from Fk and Lk. So that's the reason why we introduced this kind of chord index. And a very interesting point is if Fk is minimal, I mean, the minimal means that it has the minimal real closing points, then all the minimal diagrams of K have the same rise. The reader are suggested to compare this result with the classical result that the minimal diagram of alternating node, all the minimal diagram of alternating node have the same rise. Yeah, if it is minimal, because the minimal alternating diagram may be not unical, but they all have the same rise. So I think that's all I want to show you about the chord index invariance of virtual nodes. Thank you very much.